Hello, everyone, and welcome back to this video series talking about nitrogen processes using the HBV BioRT model. So in the previous video, we have walked through the background and theories of two shallow zone nitrogen processes, the soil and leaching process, as well as the plant nitrate uptake process. So continuing with the previous video, I will show you how the process is actually set up and ran in the BioRT-HBV model using the soil and leaching process as my focus point. So to run the actual BioRT model, there are 9 input files that we need to alter and set up, which I currently has listed out in the slides. For a more detailed rundown of what each input file is, please refer to the BioRT-HBV input files video in the previous section of this video series. For my purpose of my videos, I will only be talking about the components that we had to change and set up to run the nitrogen processes. Also, a quick note, this is under the assumption that we already have our HBV model portion ran, and we already have the input files that are associated with the HBV setups already set and complete. So to start off, the first input file that we need to change is what we call the chem.txt file. So how this video series is going to work is I will show you the setup of my already filled out chem input files, and then walk through the different important components. So to start off, here is showing my setup chem.txt files. And let me get out my laser pointer. So the first thing that we're going to look at is for our within our chem.txt file is this upper portion. So in this upper portion, there are really 3 important steps that we need to make sure of or double check. The first one is where it indicates as the transport only. The value next to this column should be a 0, which indicates that we are turning on our reactions. So for our soil and leaching process, it does involve reactions. So we must be checking that our reactions are turned on. If we have a 1 next to it, then we're indicating that it's only a transport-only reaction, which is only suitable for stable isotope tracers or some kind of, or those kinds of experiments. The next thing that we need to double check is that our precip chem, it is indicating a 1 here, which is we're using a time series to analogize our model. And then our num-exp is indicating a 1, which is indicating that we are using a numerical experiment to model the BioRT model. Once again, these, if you're confused or need to familiarize with any of these terms, please refer back to the BioRT-HBV input files video for a better explanation of what these are indicating. Okay, so then moving on, the next process or next component that we need to look at for our chem.txt file is to define our primary and secondary species. So really quickly, primary species can be thought of independent species for a reaction. And then secondary species are the species that depend on those primary species through laws of mass action. Secondary species are usually more important in terms of watering reactions, and it is something that we do not have to worry about for our nitrogen process for our video. So as you can see, our secondary species is currently blank here. And then we need to list out our primary species. So looking at the soil and leaching process reaction network, there are essentially 2 primary species that we need to account for, the soil and solid, as well as the nitrate. pH is included in this list as a requirement for the model to actually. And lastly, we need to identify our mineral kinetics, which we'll be using for our reaction. In this file, we just need to identify the mineral kinetics name, which will correspond to the mineral kinetics set up in the CDBS or the database file. Here I label my mineral kinetics as the default for the soil and leaching process. Really quickly, for folks that are unfamiliarized with the input files or are new to this model, we can jump into the CDBX and look at what the actual mineral kinetics looks like for soil and so here is the corresponding CDBS label for the soil and solid. As we can see, here is the label, which is the default, which is what we indicated in our chem.txt file. And then some kind of important types. This is indicating that the mineral kinetic is monad. We had the defined K rates in log form and as well as monad terms. So with these three components, we have the chem.txt file set up for the soil and leaching process. So after the chem.txt file, the next step is to set up our CINI file, which is what we use to set up the initial concentrations for all the defined species in the three zones: the precipitation, the upper zone, or the soil shallow zone, as well as the lower zone, which is referring to the deeper zone, as well as set up the reaction rates parameters for any defined soil phase, solid phase minerals. So here is my setup CINI.txt file, which I have the input of some of the initial concentration values and reaction rate parameters. So looking at the breakdown of the CINI.txt file, first of all, we have the three zones label: the precipitation, the upper zone, and the lower zone. And then we also have the listed out of the three of the species that we indicated within our chem.txt file. Though the order of the species on label does not really matter, it is a common good practice to have all the aqueous species listed first, and then the solid phase species on the bottom of the list, and then have the corresponding reaction rate parameters. So this is just showing that. So like here I have the aqueous species listed out on the top, and then my N, which is the solid phase, and then the reaction rate parameters listed out in response and corresponding to the solid phase minerals. So after that, let's look at the reaction rate parameters. If we recall from the last video, the monad reaction rate is what we're going to use to define our soil and leaching process. So this SSA, which stands for specific surface area, is and corresponding to the area term here in the reaction rate equation. We have the log K term, which directly refers to the reaction rate constant. Next, we have this Q10 term here, which is the parameter that we use to define our temperature sensitivity. So in general, the temperature sensitivity function is following the Q10 base form defined in literature. And we are basically trying to define this Q10 term here in our parameters, which represent the relative increase in reaction rate when the temperature increases by 10 degrees Celsius. So then the next two parameters here that we have will define our soil moisture sensitivity. So basically, in general terms, the soil moisture sensitivity factor is a function of three components. First, we have this SW term, which stands for the actual soil moisture. We have this SW, term, which is standing for the critical soil moisture term. And then we have this N component, which is a exponent. So what we're trying to indicate here is that at some critical soil moisture value, when the soil moisture is below this value, the decomposition rate is slower because the reactions are limited by the amount of water available. And then when the soil moisture value is above this critical soil moisture value, decomposition rates get slower because soil pores are filled with water, and the reactions will be limited by the availability of O2 oxygen. So there is this intermediate soil moisture zone where the reaction rates reaches their maximum. And then this N exponent is just a sensitivity index that reflects the magnitude of the rate dependence of soil moisture. So if we look back at our reaction rate parameters again, this SW threshold is referring back to this critical soil moisture term that we were talking about. And then this SWAXP is this N term, this exponent term that we're referring to. And then lastly, we have this N alpha term, which reflects a reaction rate that depends on the water table depth. However, in this tutorial, we are going to assume that the reactivity of the soil and solid does not change with the depth of the water table, and thus a 0 value is placed here as a placeholder. Oops, sorry. So now that all the parameters are explained, let's look at the values that I actually inputted in this Cine text TSC file and point out some of the key aspects. So aqueous species, the initial concentrations can be based on measurement data, but the important focus here are the mineral concentrations, the soil and solid for our case here. So we inputted an extremely small concentration and SSA value for the soil and in the precipitation zone, indicating a negligible concentration because the model itself does not take a 0 as an input. Soil and leaching process primarily concentrate in the upper zone. Hence, we have an extremely high soil and concentration in the upper zone, as well as a high SSA value. In the lower zone, we speculate that the soil and leaching process are much less prevalent as microbial abundance decreases, but soil and leaching processes could still occur, say from rock weathering processes. Hence, in the lower zone, we have a much smaller magnitude concentration of soil and SSA in comparison to the upper zone, emphasizing that most soil and leaching processes are occurring from the upper zone of the soil. And the parameter values can be later adjusted via calibration processes. So these values here right now are just indicating initial values for a starting point. The last piece of input file to alter is what we call the num.exp precip.chem, as well as the precip.chem.txt files. So a couple of reminders, the precip.chem.txt file and then the num.exp precip.chem.txt file should be the same. There should be separate columns for each solid and / soil solid minerals that you listed out in your chem.txt file. So as you can see for my example, I have the pH, I have the nitrate, as well as the soil and solid. And then it should follow a daily time scale that matches with the time sets from your HBV results. So with that said, the other input files should be kept the same. Again, if you need a refresher on what the remaining input files are, please refer back to the BioRT-HBV input files video. And then now with these input files ready, we could run the model, the actual BioRT model for the soil and leaching process, which we will do in the next video.